in 2014, a small London startup by the name of DeepMind was acquired by Google for $500 million. Now that is a lot of money. For what it seemed to be a simple program was a bot for Atari games. The reason Google paid so much for it was because it was one of the first steps towards something called general artificial intelligence, which is something that can not only excel in one task, but multiple tasks. So generally speaking, its capabilities are generalized, just as humans are. So, and they called their bot the Deep Q Learner. Before we get into Deep Q Learning or Q Learning, let me first introduce the concept of reinforcement learning. So we're very familiar with supervised and unsupervised machine learning models, but reinforcement learning is way out there. So with supervised model, you usually are trying to learn a function that's able to map X to Y. And with unsupervised machine learning models, although there are no labels, sometimes we have a transform function which takes in some input sample X and turns into a representation called Z. PCAs, autoencoders, and restricted Boltzmann machines are some example algorithms that do this. And in contrast, we have algorithms such as k-mean clustering, Gaussian mixed models that have the fit function, but they don't really, we're not trying to predict anything with it. They're trying, basically, we can learn something from the data, such as what cluster the data belongs to, or what variance of that cluster is. So reinforcement learning is very different. So reinforcement learning is able to teach an agent how to act in the real world. It's a big leap from unsupervised and supervised machine learning models, not only because the interface is no longer just data. Interface is so much broader. It's the entire environment, but also because the way that reinforcement learning agent learn is totally different. So what you have is an agent and environment, and the environment is going to give the agent a state S at time t, and the agent is going to take an action at time t, and the environment is going to return a reward as well as the state at the next time step accordingly to the reward. So what does this all mean? So let's boil this down to a small, very simple project where we're going to build an intelligent tic-tac-toe agent. So there are 4 aspects I'm going to go into. So in terms of environment and agents, we have the agent class and the human class and the environment class. The environment class is basically how the game works. So we have various methods, including the initialize function, the reward function, the get state function, as well as the board, which is basically how the game works. Then we have state enumeration. Now this is very interesting. So how do we represent our states? How do we quantify like this game into something that the agent can understand? So we can represent our state by a 2D tuple by the size of 3 multiplied by 3. So now each state maps into a number, and we can store the value function in a NumPy array. So in order to initialize our value function, we need to enumerate our states. So there are 2 ways to go about this. First, we can search the decision tree, or we can find the state board permutation. So which way is the optimal way? Now let's see. So if we were to search decision tree, at the start we have 9 choices. Now after time step 1, we have 8 choices, and then 7, and so on. So the total number of tree nodes here is the factorial of 9. But if we were to look at the diagram on the left, we can see that as the tree branches out, it repeats itself. So now this makes this model very redundant. And on the other hand, if we were to look at the number, the factorial of 9, we see that this number is super exponential. And as we all know, exponential is never good. So if we were to go to the board permutation way, now each location has 3 possibilities. So the total number of states is basically 3 to the power of 9, which is much smaller than the factorial of 9. And now we're going to the value function. So what is the value function? The value function is basically a measure of all possibilities of future rewards you might get. It's a fast and efficient way of determining which state we want to go into without searching the decision tree. So if we were to look at a diagram, let's say we're in state A, and we can go into, let's say we have state A, and we can go into either B or C. We have a 50% chance of going to B or C. So the value of state A is basically the reward from B and C multiplied by its possibilities, which gives that a 0.5. Now 0.5 compared to other state value, maybe 0.2 or 0.3, we know that state A is our optimal action, and we should go to that state. And then we have our main loop. So now we have our agent, we have our environment. It's basically the code that does the other miscancelous task that relates the 2 together. So basically keep track of players, alternate between players, and agent take actions, and it updates history. And Finally, we create two agents. We create two AIs, and then we initialize our value function, and we play 10,000 games, and we create a virtual environment every time, or new environment for every iteration. And finally, we can play against humans, and we set the variables to be true. So now we can see how the reinforcement learning agent maps out its value function. So now I'm going to do a short demo. I actually need a volunteer here. Does anyone think they're a good tic-tac-toe player? All right, Ria. Come on. Yeah. OK, so this is basically the board. And as you can see, like the value within is basically the value function of the value for each, each location. And so our reinforcement learning agent has already taken the center location. And which location do you want to take? Yeah.
Bottom left.
Bottom left. All right, give me a second.
Am I bottom? Did you put bottom right?
Yeah. Oh shoot. Yeah.
Okay, that's fine.
Yeah. Do you want to
top right.
Top right. Okay. So 0.2.
Actually, no. Oh wait, no. Right.
Wait, you have to block it, right? Okay.
The middle, like just block it in the middle.
All right. 1.0. Oops.
Bottom in the middle.
Which one? Oh yeah. Okay. 2. All right, see, so now the game is over. And we have, I don't think we have any winners here. So through this short example, we can see no matter how Ria blocks it and how, no matter what she does, the reinforcement learning agent is can lose because it has gone through 10,000 times of iteration, and now it's able to map the value function very efficiently. Thank you. So now we know we used something called the value iteration, and which can be modeled after the Bellman's equation. And we know our Q function converges to the optimal Q function as our I approaches infinity. Now this can be used for the tic-tac-toe case because the number of states in the tic-tac-toe case is very small. But if we were to do an infinite number of states, now this has totally become not feasible. So we need a function approximation to estimate the Q function. Now we think about it. What is good at handling data? As we all know here, neural networks. So for my next project demo, which is using reinforcement learning for trading, we're going to use something called recurrent neural networks. In the usual feed-forward neural networks, it only accepts fixed-size vectors as inputs. And the hidden state, it's only based on input data. It doesn't have sequences. Thus, this is not applicable to time series predictions. And we need a way for information to persist. Now, recurrent neural networks accept sequences of vectors as inputs. So in a feed-forward neural networks, we have input going through hidden state, then we get output. In recurrent neural networks, we have input plus the previous hidden state, and then going through hidden layers, and we get the output. So the hidden state is basically a combination of the input data at current time step and the input layer at the previous time step. And we can model this mathematically. And then we realize we have this problem of decay of information. So as our data fade into the past, it becomes subtle. It becomes very subtle because our error signals from later time steps cannot make it back far enough to influence the network at previous time steps. And this is called the vanishing gradient problem. How do we solve this? So we know in your usual neural networks, neurons are basically units that are applied some sort of activation function, such as a sigmoid function, to its linear combination. Now we come up with something called long short-term memory cells. So in long short-term memory cells, it has an input gate and output gate and an internal state that fit back into itself across multiple time steps. So when it feeds back into itself, it has a constant weight of 1. So we know when arrow multiplied by 1, the value does not change. So now we know it's able to solve the vanishing gradient problem because now we know that any data fed into this recurrent unit, it's preserved indefinitely. So now with this update, we're able to, our neural networks is able to remember long-term dependencies, and now we're able to apply to time series predictions. And we combining it with our reinforcement learning agent, we have our deep reinforcement learning agent. And now we're going to apply it to the problem of trading. So I'm going to the data procedures first. So I used the Bitcoin daily price as my price inputs. I got it from the Kraken via Quandl. And then we split the data by an integer value of 0.8. And then in terms of environment state, now here we're modeling after a risk-neutral investor. So we're trying to maximize final wealth as opposed to maximizing the expected utility of final wealth if you're modeling a risk-averse investor. And the reward here now naturally becomes marginal wealth, which can basically be modeled after that equation, which equals the change in portfolio value. And now in terms of the inputs we feed into the recurrent neural networks, aside from daily price, I also fed in many technical indicators, which include moving averages, relative strength index, standard deviation, and Wheeling percentage range. And now here's our Q function, which is basically a recurrent neural networks with 2 layers with 64 neurons in each layer. And we also use a technique called experience relay, which basically make each update batch bigger, now making this neural network update more efficient. And now I go ahead and run it because it takes a really long time to run it. And here's our result. It is very interesting. I would definitely say it's not applicable to the real market because I ignored the slippage as well as transaction costs in this case. But I think this result is very interesting and it's definitely show that reinforcement learning can definitely be applied to the problem of trading. Now, in terms of trading, trading is a very interesting problem because it has a large amount of data set and it follows a Markov decision process. Now, if reinforcement learning can be applied to the problem of trading, it shows its numerous potentials. It can affect inventory management industry, as well as manufacturing industry, as well as the delivery management industry. So again, reinforcement learning is one step further into something called general artificial intelligence. It's definitely something about to be more explored, and it's subjected to exponential growth in the future. So yeah, thank you.